So this is all this calculus about MC delta T, and that's the formula that we need. And the other thing is then, so this is where your substance is in one phase and the temperature is rising. But when you're melting ice, when there's phase tension, the temperature remains constant at 0 degrees centigrade. So you can have ice at 0 degrees centigrade and you have water at 0 degrees centigrade. So as you are melting, there's no change in temperature, but yet the substance would absorb heat. So in that case, we use the formula M into delta H. Okay. So if you look at this, the situation here, that here you are, ice is melting, and if you put a thermometer here, as long as ice, the temperature will hold at 0 degrees centigrade. Okay, but it is still absorbing heat, and this is called the heat of fusion. Fusion means melting. Okay, uh, and this heat is used to overcome the intermolecular forces. Okay, uh, but the temperature is still the same at 0 degrees centigrade. And so if you do a heating curve, like if I take ice at minus 20 degrees centigrade, okay, and if I heat it, so on the x-axis you have heat added and the temperature on the y-axis, you can see that gradually the temperature of ice is going to rise from minus 20 and will reach 0. So as soon as it reaches 0, it will start to melt. And even though it is absorbing heat, there is no change in temperature. It's remaining horizontal. And then when all the ice has melted, the temperature, so everything is water now at this point. And so it will rise from there and will start rising and go all the way, it can go all the way up to 100 degrees centigrade when it will start to boil. Now, when it starts to boil, again, the temperature will become constant. But if you look at this part, the melting curve of ice, so this horizontal part is where the ice is melting. Okay. Uh, so this is how all heating curves will look like when there's a phase tension. Okay, and if you do that for water and up to the boiling, and then at boiling, the temperature will again go constant. And this is general nature. Now at this point where it is melting, the temperature is not changing, but it is still absorbing. And so we define another kind of heat, which is the heat of fusion, which is basically defined as the amount of heat required to melt 1 mole. Now we haven't done mole, okay, but you can also define it as 1 gram. So 1 gram. For ice, that's like 80 calories per gram. So in order to melt ice at 0 degrees centigrade to water at 0 degrees centigrade, that is the amount of heat you have to give. In joules, we say 6.02 kilojoules per mole. Now again, we'll learn about mole in later chapters. Okay, but we can also have this in grams. Okay, uh, and the so when it is melting, it is absorbing heat, and the reverse, that when you are freezing, it will give the same amount of heat. It's basically equal and opposite sign, and it's called the delta H fusion or heat of fusion. Okay, and if you are doing it in grams, like 6.02 joules per gram, then if I get 10 grams of ice and I want to melt it, okay, so it will be 60.2 kilojoules. Okay, and there's no delta T term because there is no change of temperature. So the delta H is negative because is exothermic. So exothermic means heat is given out from the ice. So it's losing, okay, it's a loss of heat. And that's why it is negative. That's why it is negative. So the sign convention also need to be considered here. Okay, now here's a simple question uh, that calculate the amount of ice in grams that upon melting absorbs 237 kilojoules of it. Now the heat of fusion is in kilojoules per mole. Now take it for granted for now that 1 mole of water is 18.02 grams. And I'll tell you later how we come to that values. But uh, when I give you questions for this, I will give you in grams. Okay, so not moles. Uh, so basically, uh, you are multiplying and canceling the units, and you are getting 709 grams. Now, if I give you in grams, like the same questions, calculate the amount of ice in grams that upon melting will absorb 237 kilojoules of heat. But instead of saying 1 mole, I would say um, for this one 80. So 18 to 4.18, that's 332, I think. 334.7. So 334, let's say 334 joules per gram. Okay, so if I give you this, um, then how do you calculate? Uh, so uh, 237 kilojoules, right? 237 kilojoules. Now, kilo is 10 to the power 3. So you have to have everything in joules. Okay, so we'll write 10 to the power 3 joules. And my heat capacity is 334 joules. Okay, hold on. How do we use this? So in order to convert, I will first place my units. Okay, so I need to cancel out the joules. I need the answer in grams. So if you look here, 334 joules per gram, that means 334 comes here per 1 gram. So your joule and joule cancels out. And if you calculate, how much do you get? 237,000, right? 237,000 divided by 334. So I'm getting 709.5. So actually this is 334.7. If you put that number here, probably we'll get closer to that value. Let's type that. 237,000 divided by 334.7 is 708. So that one came out 709.5. This 708. So kind of close. But again, this is how you do it. Just follow the units, simple calculations. Just don't make careless mistake. Follow the units. Okay. Now we'll look at few other things here. Evaporation. We all know what evaporation is, but we'll look at it scientifically. That what happens during evaporation. Okay. So evaporation. So we have one thing is boiling. What evaporation, like you are trying to dry clothes. Okay, so you just leave the cloth and water evaporates out. So evaporation happens from the surface of water. So if you look at this beaker of water here, okay, this the water molecules are attracted by all of the molecules around it. So if you just look at one of them, okay, but if you look at the surface, only water that are below it are attracting. Okay, and because of that, the water molecules are held less tightly at the surface. Now, what happens is everything is in motion, as I said, because there's a temperature. Unless until is absolute zero, everything has a energy. Now, if you draw the kinetic energy profile, okay, and if you see, you can see that in this graph here. So on the y-axis, you have fraction of molecules. And on the x-axis, you have kinetic energy. And if the blue line is the lower temperature, and this is how the graph look like. Okay, we say Gaussian curve. Now, to escape from the surface, the molecules need a certain amount of energy, and that is shown by the dotted lines. And if you look here, the shaded region are the molecules that possess that has that much amount of energy to escape. Now, if I raise the temperature, now the kinetic energy of the molecules changes, and the energy profile now looks like the red line. Now you have more molecules within this area that has the energy to escape. And that is why the rate of evaporation increases with temperature. So if I increase the temperature, if you are using a dryer, let's say, you are evaporating, right? In the dryer, if you increase the temperature, it gets dried faster. And that's because you are giving the molecules more energy to escape. Okay. Now, another term is the condensation, is the opposite of evaporation, where the water vapor condenses back to liquid. And these are opposites. Okay, these are opposites. And so often we talk about dynamic equilibrium. What is the dynamic equilibrium? So if you look at the situation here, okay, so this is a conical flask where you just took some water. At the very beginning, okay, the water molecules will try to escape and it's stoppered, so they're going to get trapped. Okay, and the vapor is going to collect over the top of the water. Now, as more and more vapor gets collected, they'll try to condense back to the liquid. So there is always two opposing things going on. So there is always some evaporation happening and some condensation happening. At the very beginning, in situation A, things are all evaporating. But as you know, uh, molecules accumulate in the vapor phase, they also start to come back, okay, to the liquid state. That means and these two processes, okay, eventually becomes equal, and we say equilibrium is established. So equilibrium is a situation where two opposing processes, has the same rate. And this is called dynamic because you will see nothing is changing. But nothing is changing apparently to rise, but the two processes are going on in equal and opposite directions. It's like the freeway. The cars are moving in both directions. That's why no car is accumulating. Okay. Apparently, if somebody is counting the car over a unit area, they will see the number of cars is same. So it's equilibrium. But it's dynamic because cars are moving in and out at the same rate. And same here. Your water molecules are condensing and water molecules are evaporating, and they are doing so at the same rate. So that's why it's called dynamic equilibrium. So remember this term, dynamic equilibrium. Okay. So just like freezing and melting, so we have solid, and solid becomes liquid, and liquid becomes gas. So each of these processes, need heat. You have to heat them. So these are all endothermic. So if you look at, so this is what we call melting. This is melting, and liquid to gas is evaporation. Okay. So these are endothermic processes because they are absorbing heat. On the other hand, if the gas condenses to liquid, it is going to give heat. So heat is given out. So these are all exothermic. So this is something you should remember. Okay, you might get questions from here. So gas to liquid is condensation. The condensation is an endothermic process. Okay, while evaporation is a endothermic. And if you look from solid to liquid, again, heat is given out. And so these are all exothermic processes, the one at the bottom. So when you look at melting and evaporation, they are endothermic, while uh, condensation and liquid to solid is freezing. Okay, freezing is a exothermic process because heat is given out from the system. Now, another thing is sublimation. Sublimation, so oftentimes, sometimes we'll see solid, directly converting to gas. So, so this process without going through liquid state, and this process is called sublimation. And this is dry ice, solid carbon dioxide, uh, you know, and it can directly go from solid to liquid state without having a liquid state. Okay, so that's why it's called um, dry ice. So if you have dry ice, it will directly become gas without having liquid. So we can also see that to some extent in water. Okay, so if you keep ice um, in the refrigerator open, it often dries out, becomes smaller and smaller because of sublimation. Some amount of sublimation is always happening. Now we'll discuss, so before we go there, uh, so we discussed the heat of fusion. Similarly, you can have heat of vaporization. And for water, that is 40.7 kilojoules per mole or 2.26 kilojoules per gram. Okay, so if we are using, since we are not using moles at this point, because we don't know moles, we'll be using this 2.26 kilojoules per gram. 2.26 kilojoules, 2.26 calories, I think calories, sorry, calorie, kilocalorie per mole. 2.26 kilojoules per mole, because one mole is 18 point, if you divide by 18.02 grams, okay, that is what you get. All right. Now, we'll come back to some calculations here. But before that, let's look at this, the boiling and vapor process. So whenever you keep a liquid, there's always some vapor accumulated on the top. Okay. And that, the pressure exerted by that vapor is called the vapor pressure. Okay, so for atmosphere, so normal atmospheric pressure is 760 millimeter of mercury, or we say one atmospheric pressure. Okay, and there's always some vapor in there, and that fraction contributed by the vapor is called the vapor pressure. A fraction of the total pressure. Okay, so the vapor pressure. So if more and more vapors are there, there will be more pressure. So the vapor pressure increases as evaporation increases. That means if I increase the temperature, the vapor pressure will increase because there is more evaporation. And if the intermolecular forces, that is the forces that are holding the molecules together, if I reduce that somehow, then the liquid becomes more volatile. Like you can think of acetone or chloroform, they're very volatile liquid. And the vapor pressure is going to increase. Okay. So when you think of boiling, so you are heating it and you are giving it sufficient energy that it can turn into vapor from all parts of the liquid. So that is what is different from evaporation. Sorry. So evaporation is happening only from the surface, but boiling happens from everywhere. And if you look at the bubbles, they're not air. Okay, when you see bubbles coming out from boiling water, so you have the vapor of water inside. Okay, and that rises and that tries to escape into the atmosphere. So remember that there's no air inside, but water vapor inside the bubble. So if you look at the heats of vaporization, and we'll talk about intermolecular forces in later chapters. That depends on the chemical structure and other things, that the forces that are holding the molecules together, and there are ways of figuring them out. So the delta H vaporization and delta H um, fusion are also indications of those intermolecular forces. So greater the this heat of evaporation and heat of fusion, the greater will be the forces of attractions, the intermolecular forces. And we can see that in some of the common liquid that we know. Okay, so these are the normal boiling points, and you can see the boiling point is so low for diethyl ether, acetone, isopropyl alcohol, much lower than that of water. Okay, water is 100. Okay, and the heat of evaporations are also higher. Okay, so there is a kind of a relationship there between the boiling point, the force of interactions, um, heat of evaporation, heat of condensations, and so on. Okay, so because more heat is required, it requires more energy to overcome those intermolecular forces. So think of it that way. Now, if you look at the heating curve of water, so you saw that for ice, now it is for water. So you are increasing the temperature from 20 degree, to all the way to 140 degree. So if you want to calculate how much heat is required, you have to basically divide it into three segments. Okay, these segments are Q1, okay, and this is Q2, and this is Q3. So each segment, there's a different amount of heat that is absorbed. So Q1 is water. That means um, I can write, if M is my mass, C is the specific heat capacity of water, okay, and delta T, how much is the delta T? So if I say that this is the delta T, delta T1, okay, and this is the delta T2. So delta T1 is the temperature to which you have raised the temperature of water. Okay, so this is the delta T1. And Q2, so what is my Q2? Is the melting, or in this case, boiling, not melting, but melting is basically the same idea. So Q2 equal to M multiplied by delta H. So in this case, is delta H of evaporation. And Q3 is M is now steam, right? So M multiplied by C of steam, and that multiplied by delta, sorry, this one is T1, delta T2. So you have to always cut them into segments, okay, and then add them. So Q equal to total heat equal to Q1 plus Q2 plus Q3. So you have to just do the math systematically. That's all. Easy math, but just systematic. You have to compute Q1, Q2, Q3 separately and then add them up. Now, things to remember here is the delta T. So here the delta T1, how much is delta T1? Delta T1 is equal to 100 minus 0. So this many degrees centigrade. Okay. And your T2, your delta T2 is 140, right? 140 minus 100. So these are the two things that you need to be careful about. Okay, the difference of temperature. Because it's steam at 100 degrees centigrade, where we are heating to 140 degrees centigrade. So here you have a question that calculate the amount of water in grams that can be vaporized to its boiling point uh, vaporized at its boiling point with 155 kilojoules of heat. Now here again, we can basically use that 1 gram is 2.26 kilojoules instead of mole. Okay, instead of mole, we can use this. So you don't need this one now. Okay, so you can multiply this with 155 kilojoules. Okay, and that will be, you'll get the same answer. You can try that in your calculator. So remember, because this kilo and I have this kilo, this is canceling out. Otherwise, I might have to convert the kilojoules to joules, okay, by multiplying with 10 to the power 3. Now, this is the whole thing, starting from ice all the way to, uh, you know, all the way to you are going um, to steam here, right? Um, and and if you see, this is my Q1 and this is my Q2. No, this is my Q2 right here. Okay, this is my Q3. This is the Q4 and this is Q5. So I have to basically add 5 things here. Now, right here, everything is steam. Okay, so this is steam. So you have to use the specific heat capacity of steam. Okay, and your delta T. So this is your delta T, right? So if I write it here, so this is a delta T3, change of temperature, and that you are going to use for the steam. Now, if you come down here, this is a delta T2. Now, this is for water. Right here, you're going to use Q4 equal to, it's basically boiling. So this is basically the boiling. That means the temperature is remaining constant at this point. Okay. Um, and Q4 equal to M multiplied by delta H, and delta H of vaporization. And in all other cases, we're going to use Q equal to MC delta T. So here, this is water. So basically, we are heating water. Okay. So this is the uh, CW. Okay. And we are using T2. This is for the steam. So we have to use the heat capacity of steam for Q5. Now here, this is M delta H fusion. Fusion is that for melting. And this Q1 will be same as Q3, Q5, and Q1, but they are for ice, water, and steam. So if I give you all these parameters, you should be able to just multiply and add them together. Okay, and the total heat will be the sum of all this. So so this is all about this chapter. Okay, so yeah. So if you go to this PDF, there's some extra things here. Okay, heat. Sorry, energy and nutrition. That section is not there in the slide. Okay, so I included them in the PDF. So this PDF is basically a summary. Uh, the classification of matter. I'm not going over this. Uh, and then you have the states of matter, solid, liquid, gas, physical properties, chemical changes, temperature scales. Okay. So in the temperature scale, you know, you do not have to look at the blue one because it's like how we got to that formula. that you are using for conversion. But if you want to look at it, you are welcome. Okay, that's why I have it in different color, but it says how we got to the formula. It's basically a solution of a straight line. That's all. Equation of a straight line. Very simple. But if you want to know, I can quickly tell that. Uh, so when you're thinking of ice, so that's one point in the graph, right? So ice, I can have 0 degree centigrade, or I can say 32 degree Fahrenheit. So these are my points here. So these are my points. If you think, so if you think that this is a straight line, this is my point on ice, 0 degree and 32 degree. Okay, so X and Y. And if I think boiling water, this is another point, which is 100 degree and 212 degree. So you have 2 points, and if you remember how to do that from your algebra class, actually, the Math 2. Uh, so we say uh, uh, 2 point equation. From 2 points, can we generate equation of a straight line? So and that is the formula I use. Okay, x minus x1 divided by y minus y1 divided by x minus x1 equal to slope of the line. But again, you don't need to. So this is not part of the course. But if you want to know how we got this formula, only then, as extra studies. Uh, and this is what I want to point out: energy, okay, kinetic potential, the conservation of energy, units of energy, and the conversions, okay, um, and then heat and calorimetry. Calorimetry is what you actually saw in the video, okay, that when you are taking water, adding hot metal into it, you are doing calorimetry. So calorimetry is basically a measurement of heat, technique of measurement of heat. Uh, all right. So again, okay, this is what I wanted to calorimetry, and then energy and nutrition. We haven't talked about that, but there's something that uh, people going into medicals also interested in all these nutritions and things would need. Now, very simple. So when you burn in a carbohydrate, so for every gram of carbohydrate is 4 kilocalories. So we say 449. 449 carbohydrate and protein is 4, fat is 9 kilo. That's the amount of energy you get. Okay. And in joules, kilojoules is there. So just remember the calories. Okay. Um, so now if you have like a food where we know how much carbohydrate, fat, and proteins are there, you can easily calculate the total calories. And this is part of this course. Okay, calculation of calories. Um, so here are some examples. It's simple. Simply you multiply. Okay, like hamburger contains 17 grams of carbohydrate, 19 grams of fat, and 23 grams of protein. What is the energy from each food type? Yeah, so basically simply multiply them, and then you get the energy, add them up, 400 kilocalories. Now again, nutrition, remember there's a big cal, which is 1,000 kilocalories, means 1,000 calories. Means 1 kilocalorie is big cal, big C, okay, calorie big C. Uh, so this is additional thing that is not there in the slide. Remember, it's not there in the slide, it's here, okay?
Okay.
Uh, and so you can try any of these books that are showed in the liver text. Practice their examples. There are a lot of examples there. So if you are confused, look at the examples in those books. Okay, how they're doing it. And then there are the videos that I gave you.